So now we're going to practice graphing. We're going to do a rational function. This one's going to be pretty complex because, as you know, with rational functions, there's vertical asymptotes, there's horizontal asymptotes. Each of those is going to require us to look into limits. So this will take a little bit of time, and we can do this. All right, you can do this. I have absolute faith that you can do this on your own. So let's get started. We're going to go through all of these steps. Again, if your teacher just says, tell me where it's concave up or concave down, you skip straight to the second derivative, do your sign chart, see how that works. If they want to know where it's increasing and decreasing, then you go straight to the first derivative, find your sign charts. If they want to know about the limits, you're going to go around the vertical asymptotes and talk about horizontal asymptotes. So you most likely will not have to do all of this at one time, but you'll do parts of it. So use the appropriate parts. And if you happen to be in my class, yes, you do all of it. All right, so here we go. I know, terrible. All right, so if we have f of x is equal to 5x over 5x squared minus 125. Now, we could go through all of these derivatives and everything else that we're going to do, limits, x-intercepts, y-intercepts, but do you notice how there's a 5 in common all the way around? So we could make it slightly easier on ourselves if we factored that out and reduce. So you can do that. I just wanted you to know. Now we're going to start and we're going to go through our list. So the first thing we're going to talk about is the domain. And you remember from algebra days that the domain is assumed to be all real numbers from negative infinity to infinity unless you have square roots in the bottom. I'm sorry, unless you have variables in the bottom or square roots. Sometimes you can have square roots in the bottom. And then there may be another case or two. And there's also restrictions on the domain when you have trig functions that are not continuous. So, but let's just talk about the one with variables in the denominator. So if you have variables in the denominator, you know that the denominator cannot be equal to 0. So x squared cannot be equal to 25. X cannot be equal to plus or minus 5. Now, when they ask about the domain, they don't want to know what you can't have. Now, sure, sometimes people say, tell me about the domain restrictions. But when they're asking about the domain, they are technically asking what can you have, what is included. And so you would say, well, I can't have plus or minus 5, so it's negative infinity to minus 5, minus 5 to 5, and 5 to infinity. And you can see the holes here at 5 and negative 5. And it depends on how your teacher wants it expressed. If this is interval form, or if they want it expressed in set form or something, you will know by now because your teacher will have demonstrated it. Now, how do you find anybody's x-intercept? You set y to be 0. So you would say 0 equals x over x squared minus 25. And if you're going to have something equal to 0, it's the numerator that has to be equal to 0. So x is 0. Now, again, some teachers will accept that x is 0 is the x-intercept, and some want to see the point itself. So if x is 0 and you set y to be 0, this is your ordered pair. And then for a y-intercept, you set x to be 0. So y would be, excuse me, 0 over 0 squared minus 25. So y is 0. And if your teacher wants an ordered pair, you had set x to be 0 and you found y to be 0. We're going to talk about symmetry. And to decide about symmetry, you're going to take your function, which was x over x squared minus 25. And everywhere you see an x, you're going to replace it with, excuse me, a negative x. And simplify as best you can. So you have negative x over x squared minus 25. Now, as you can see, the denominators match from the original to the one that we obtained with the negative x, but the numerator is the opposite of what it was. So this is the opposite sign, right? Because technically here you had a positive version of this, and here you have a negative version of this, right? So it's the opposite of what you started with, so it's odd, which is symmetric with respect to the origin. So getting the opposite of what you started with and origin both start with O, maybe that'll help you to remember. And periodicity. There is no period in a rational function, and that would be your explanation. And then we're going to talk about vertical asymptotes. Now you get your vertical asymptotes from restrictions on the domain, and in this case from what you couldn't have in the denominator. So your vertical asymptotes up here in the domain. Okay, up here in the domain, you tell me what you cannot have, right? See the not, x cannot be equal to plus or minus 5. And then you tell me all the other numbers. But down here, I'm asking you where the vertical asymptotes are. So they are at x is plus or minus 5. So there's not a not. Okay, so this would be incorrect because I want to know where they are, right? If you put the not in there, you're telling me where they're not at. So one of the things was if we found a vertical asymptote, we were going to talk about the limits. So here we go. So what's a limit as x approaches negative 5 from the left? I need to box this in while I'm here. Of x over x squared minus 25. And if you remember from the previous videos when we were talking about limits, you're really wanting to know about generalities, not specific numbers. And so sometimes what I do is I go, all right, so this is going to be approaching a negative 5 from the left. You're going to have a negative number. Excuse me, I'm trying really hard not to sneeze. Okay, so you're going to have a negative number in the top over, excuse me, so you would have negative 5 from the left, right here, is something like negative 5.001. So negative 5.001 squared is slightly bigger than 25. So you're going to have a plus right here. So this is going to be a positive tiny number. A negative infinity, because taking any number up here and dividing by a wee little tiny number is going to give you a huge number, and it happens to be negative. So the limit as x approaches negative 5 from the left of x over x squared minus 25 is negative infinity. All right. So then you have the limit as x approaches negative 5 from the right. And negative 5 from the right would be something like negative 4.99. So you would have a negative 4.99 on the top. And on the bottom, negative 4.99 is slightly under 5, so it's slightly under 25 after you square it, so it's a negative tiny number. And when you divide by a wee little tiny number, like 0.001 or something, you're going to end up with a huge number after you divide it in. So this is going to be positive infinity. And the limit as x approaches positive 5 from the left of x over x squared minus 25. Okay, so positive 5 from the left is something like 4.99. So you'd have a positive 4.99 over something slightly less than 5 squared is something slightly less than 25. So you're going to have a negative tiny number. And dividing a positive number by a tiny number gets you a huge number that happens to be negative. So you would have negative infinity. And then the limit as x approaches 5 from the right would be something like 5.001 up here, a number to the right. Sometimes it just helps to have an assist because these get so complicated your brain sort of goes, wait a minute, I'm not sure about left and right. So 5.001 is positive on the top. 5.001 slightly bigger than 5. So when you square it, it's slightly bigger than 25. So you're going to have a tiny positive. So the limit as x approaches 5 from the right of x over x squared minus 25 is positive infinity. Okay, so far so good. Now then we're going to talk about horizontal asymptotes. Now horizontal asymptotes are typically, you have some sort of a function, and as it goes way out here, it approaches some y value, right? And so they're talking about the behavior out here as you approach infinities. So to find the horizontals, you would have the limit as x goes to infinity of x over x squared minus 25. And you'll remember this is why I made that big gap. You're going to divide by the biggest powered term in the bottom all the way around. And so this would be the limit as x goes to infinity of 1 over x over 1 minus 25 over x squared. And dividing by a huge number, dividing by infinity, this is going to go to 0. This is going to go to 0 a little slower, but still get to 0. So this is 0. So the limit as x goes to infinity of x over x squared minus 25. Now, you may be like, why are we having to do all of these restatements? Can't you just say equals to infinity and box it in? But again, you're going into professions if you're in calculus. You're going into professions that you have to be able to express yourself in writing and in English to where the reader who may not be as knowledgeable as you are or as familiar with things as you are, you have to be able to get a complete idea across with the least amount of work on the reader's part. So you have to practice, having lovely complete statements. So the limit as x goes to negative infinity of x over x squared minus 25. And remember, we do that technique of dividing by the biggest power term when we have rational functions we're going off to infinities. I guess we do it whether we have rational functions or not, but when we're going off to infinities. So, but we may not have a denominator to start with the biggest powered term. All right, I'm sure that kind of got stuck. Go back and watch the video over asymptotes as you're going off to, or limits as you're going off to infinity. So this turns out to be the limit as x goes to negative infinity of 1 over x over 1, because x squared over x squared is 1, minus 25 over x squared. And even if this is going off to negative infinity, the 1 over a huge negative number is still 0, because 0 is kind of neutral. This goes to 0, so 0 over anything is 0. All right. There. Okay, that's the part that is just kind of like, oh my goodness, goodness, goodness. All right, so if you need to stop the video and go get a drink of water, all right, I would totally understand. So here we go. First derivative. All right, now remember the first derivative is going to tell us about where it's increasing and decreasing. It's going to give us a hint as far as where there might be a max or a min. So here we go. So let's have a refresher. So my function was x over x squared minus 25, right? It's a 25. Looks like 15. 25. All right. So to do the derivative, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay. So when you clean this up, you get minus x squared minus 25 over x squared minus 25 squared, which is, makes you feel like, oh my goodness, I can get that. Excuse me. So you could think of this as minus x squared plus 25, right? Some of you may prefer one form over the other. But when you factor out that negative, I think you can see right here that those don't actually cancel, even if up here it's really tempting. All right, now, why did we want to do the first derivative? We want the critical values. Some people call them critical points, critical locations. We want the critical values, and that comes from where the numerator is equal to 0 and where the denominator is equal to 0, because that's where it's undefined. Well, as you can tell from here, x would be plus or minus 5i, and after you square root it. So I'm not getting any real critical values, all right? Here, these are the same ones we've been dealing with here for a while. This is where my asymptotes were, my restrictions on the domain. So the points we're going to explore are on either side of the vertical asymptotes, okay? So we're going to pick a test point. So let's look at this for just a second. This minus x squared plus 25 over x squared minus 25 squared. And let's talk about this a minute and maybe save ourselves a step or two. So can you go with me that if you take any x, no matter where you are in any of these areas here, you're going to square it, it's going to be positive even if it started off with a negative. And then adding it to 25, the part that's inside the parentheses is going to be positive no matter where you start. Then you have this negative that's outside. And no matter what's going on in here, after you square it, this is going to be a positive, right? So I don't know that we actually have to come up with numbers and test the actual numbers. If you want to do that, feel free. But I'm thinking that since this part is always going to be positive and this part is always going to be positive, and I'm always going to multiply by a negative, each one of these is negative, I'm just going to live with that. Okay? So then what we would have is in each of these areas, it is decreasing. All right? So we were at H. I guess this part here, okay, this was the first derivative. I think I skipped part I. So this, okay, I got busy talking to you and I forgot to label my parts. So this is part I. Let me make sure we started so far back up here. Okay, so H was taking the first derivative and I was the critical points. And all right, way back up there. So this is I. The critical points or values or sign chart. I just got so excited talking to you about all this stuff. All right. Now, so J was, where is it increasing? And it's not. There are no areas where it's increasing. It's only decreasing. So where is it decreasing? From negative infinity to negative 5, negative 5 to 5, and 5 to infinity, which, you know, turns out to be the domain, right? Because it's decreasing throughout. And some students will try to tell me that, well, that's negative infinity to infinity. Can't I just do that? Well, no, technically you're not. Okay, because remember right in here, there are asymptotes. And so you may be doing something like, I don't know, running downhill, but in here, you're not doing anything. There's no graph because there's vertical asymptotes. So you can't go straight from negative infinity to infinity. That would imply you could break across the vertical asymptotes. All right, so L, are there any minimums, local or absolute? And no, there's not, because I don't have any little valley areas. And are there any maximums, local or absolute? And no, there's not, because I don't have anything that looks like I might be having a little mountain or hilltop there. All right. Okay. Now, so we're moving on, and we're going to do the second derivative. All right. So we had, and I'm thinking I'm going to use the version of the first derivative that look like this rather than to have to factor out that negative. I'm going to put it back in. The nice thing about math is you're not stuck with a particular format. So if you like a different format version for the ease of use, change it back. All right. So I'm going to try to take the next derivative from this first derivative. So the second derivative, since this is a quotient, is the bottom. We're going to put it in the top. The bottom times the derivative of the top minus the top times the derivative of the bottom, which is bring the 2 down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. All of that over the bottom, squared again. Because it was squared, now we're going to square it again. So what we can do is, do you see how in the top there's an x squared minus 25 here, and an x squared minus 25 there, and a minus 2x here, and this 2x we can pull this minus that's over here. So I'm going to factor out an x squared minus 25 and that minus 2x, and that's going to leave me this x squared minus 25 from the first term minus 2 times x squared plus 25. Because remember, there's all this x here that you can factor out, over x squared minus 25 to the fourth now. So you have minus 2x times x squared minus 25 times minus x squared minus 75 over x squared minus 25 to the fourth. And see how there's an x squared minus 25 on the top and the bottom? And I could pull this negative out from here and run it in the front and have 2x times x squared plus 75 over x squared minus 25 cubed. And this is my second derivative. Okay, and then we're going to look at the critical values, critical points, critical locations, and the sign chart. Right? So you would go, okay, where is the numerator equal to 0? Well, when x is 0. X squared plus 75. Well, that would be when x squared is equal to negative 75, which says this is a non-real answer if you square root both sides, so this is not contributing. Or when the denominator's undefined, which is when it's equal to 0, and this is our now very familiar plus or minus 5. Okay, so our sign chart would look like 0, minus 5, and 5. And remember, these are actually where your vertical asymptotes are going to be, and 0 is actually a 0. Excuse me. So if you look over here at the first derivative, this one right here is always going to be positive, that x squared plus 75. But this x and this, since it's cubed, could be negative or positive. So we're going to actually go through the test. I can't find a way to make, like we did in the earlier one, where we said, oh, look, if you think about it, they're all going to be positive except for that negative in the front. So we just didn't have to go through the testing, but I think we do now. Okay, now remember, this one is always going to be positive, all right, because you take any number, square it, add it to 75. So you can have your test point, and then your signs, and then your resultant sign. Okay, so if we did, let's see, we could do -6 and -1 and 1 and maybe 6. All right. So if we use the test point of -6, then that 2x would be negative. Remember, this second factor on the top is always positive, and -6 squared is 36 minus 25 is positive. Positive cubed is still positive, so this is negative. Right? Then if x is -1, 2 times -1 is negative. The second factor is always positive. -1 squared is 1 minus 25 is negative, and negative cubed is still negative, so this is positive. And x is 1. 2 times 1 is positive. The second factor is always positive. 1 squared minus 25 is negative. Cubed is negative, so this is negative. And x is equal to 6. 2 times 6 is positive. This one's always positive. 6 squared minus 25 is positive, and if it's cubed, it's still positive. So this is positive. Now what does that say? This is concave down. This is concave up. This is concave down. And this is concave up. Okay? Now, you know how this is forecasting. I mean, we haven't gotten down there yet. But you know how when it flips from concave down to concave up, then you think, okay, there's an inflection point right here. But right here, remember, that actually requires you to touch, okay, to have a continuous function through there. If you're going up to down, it would do like this, and it flips at a legitimate point on the function, okay? But these, okay, there is no point on these asymptotes, so there is no inflection right here, okay? There is one at 0, so we're going to come down here, finish up. So where is it concave up? It is concave up where the sign chart gave us positives. So that would be between -5 and 0, and from 5 to infinity. And where is it concave down? And that would be where the sign chart gave us negatives. So that would be -infinity, -5, and 0 to 5. And then where is there an inflection point? There is not an inflection point where the asymptotes are, even though the concavity switches. It switches on either side of a barrier, right? So there is not a point there. So the only inflection point I have is at 0, 0. So then when you put all this together, and I'm going to shrink this down so you can see it. Okay, and we still can't get it to fit all on one page. See all this work that you did? That's a lot of work. All right, so when you put all of this together, let me go back up here. Keep in mind that it was decreasing throughout. You had an x and y intercept of 0, 0. Way back up here. Okay, you had an x and y intercept 0, 0. It had vertical asymptotes at plus or minus 5. It had a horizontal asymptote of y is equal to 0, decreasing throughout. Okay, and then here's my concavity. So here we go. Hopefully you've written this down. It won't do you any good really just to sit here and passively watch these videos. There's something about writing it that makes it stick longer in your brain. Okay, so here's my x is equal to 5, x is equal to -5. Here's my x-intercept, my one and only point. Now, so what you have is you know that if it's decreasing throughout and it passes through this 0, 0, you know it does this. You also know it has a horizontal asymptote of y is equal to 0. And so horizontal asymptotes are not as rigid as vertical asymptotes are. You don't cross vertical asymptotes. But horizontals, if you have an x-intercept on the horizontal, it's like your path to get across. Other places you can't. So you would take a test point and say, okay, what's going on at -6? And you're wanting to know if you're up here in this quadrant or down here. And after you do your test point, you would find out that you get a negative number. So you are actually looking something like this. So it's decreasing. Remember on our limits, we said on the left side of -infinity, it's going down. I'm sorry, on the left side of -5, it's going down to -infinity. So you could actually use your limit instead of a test point to decide if you're up here or down here, because if you're going off to -infinity, you can't be up here. That would require you to have an x-intercept to get across, and we only had the one. It was 0, 0. So you're not getting across anything. So it has to be down here. Likewise, if you looked at your limits up here around your vertical asymptote, on the right side of 5, which is right here, you're going off to positive infinity. So you know you're going off to positive infinity, but you cannot start down here and go up because that would require you to cross the x-axis. You don't have an x-intercept, so you must be up here in this section, and then you hug really close to y is equal to 0 there. And this is your graph, and I'm teaching you bad habits by not putting arrows on your x and y axis. That's a thing. I think I got it in engineering classes. Anyway, so if your teacher is rightfully upset about that and they draw arrows on everything in the class when they're demonstrating it to you, you need to put arrows on it. Okay. I just think it makes the thing look even busier and detracts from the actual function. But you do whatever your teacher says. I say this once in a while, the person with the red pen wins. I don't have the red pen for you. So if there's a disagreement between what I'm doing and demonstrating for you and what your teacher wants you to do, you will absolutely do what your teacher wants you to do because they're the one grading your work. Okay, hate to put it that bluntly. All right, but that's absolutely true. Anyway, this was, as you can tell, because even if I shrink it way down, like where you can't even read it, it just barely fits. We're in one screen, and I couldn't have read it if I had to. All right, so very involved problem, but this is really a summary of pretty much everything you've done up until this point in calculus, right? With derivatives and second derivatives and limits approaching infinity and limits on either side of a specific number. So this is actually a great review for your final. All right, you really seriously, I'm very serious about this. So even if you're not doing all of this right at this moment, you might want to come back to this at some point in time because this is everything you've done. I mean, think about it. It really is just about everything you've done up until this point. So I hope this helps you a little bit to kind of put everything together. And I will see you at the next video. All right, hope so.